Hey, good morning. Calculus 1. Let's get back to this implicit differentiation. I got one more thing I want to say about it, kind of. So, I have a relationship between x and y. It's an implicit relationship. By the way, with these different coefficients here, this happens to be an ellipse. And maybe I'm at this point, negative 2, 3. Let's just think about this a second. It's an ellipse. I think it would be centered at the origin. It would be elongated in the y direction, I believe. I'm at the point negative 2, 3. Maybe I'm right there, negative 2, 3. Anyway, if I took a derivative, I'd be finding the slope of the tangent line, of course. The derivative is the slope of the tangent line. Anyway, let's try a derivative. So what we do is we walk in here, it's an implicit derivative. So we walk in here and we take the derivative of y with respect to x. But when you run into this x term, the derivative of y the derivative of this term with respect to x is 12x. But when you do the derivative of this with respect to x, it's a y term, and so you do kind of a normal power rule, 8y. But then you have to do the derivative of the y with respect to x, dy dx. It's kind of like the chain rule. After the power rule, you do the derivative of the y with respect to x. You know, let's go across the equal sign, and we'll take the derivative of the 60. That's a 0, of course. You know, let's just back up. This is one way to think. I mean, I've taught you a couple ways to talk and think your way through these problems. One way to think is after you're finished with this problem, you have to do the chain rule, and you have to do the derivative of x with respect to x. But what is the derivative of x with respect to x? A dx over a dx, you might just call it a 1. So sometimes maybe you're not doing the chain rule, or the chain rule is just a 1. But the derivative of y with respect to x spits this out. And then that's our derivative, by the way, and we'd like to solve for it. So dy dx is, I'm going to move the 12x over. I'm going to divide by 8y, negative 12x divided by 8y. And that's the derivative. And that's the slope at any point, x and y. You know, notice it's sort of an implicit derivative. In other words, it has x's and y's in it. It's not explicitly in terms of x. You know, if I wanted the slope at this point, I would plug this point in. By the way, let's just simplify it a little bit. I can't simplify the 12 and 8. Divide 4 into negative 3x over 2y is a simplified version of that. If I evaluated it at this point, y is 3, x is negative 2. Let me try that. X is negative 2, that's a 6. Y is a 3, that's a 6. Oh, I guess the slope is 1. That's not exactly what my picture looks like. I didn't draw the greatest picture, but the slope is 1 at that point. All right, now here's what I wanted to talk to you about. Let's do a second derivative. And so this is the first derivative. Back to our, well, here it is. Back to our first derivative before we plugged in the point. I want to do a second derivative now, which we can notate the second derivative of y with respect to x again. That's sort of our notation. I don't know if I've ever showed you that. Sometimes we also just call it y double prime, the second derivative of y with respect to x again. But here I go. If I'm going to do this second derivative, it's an implicit derivative. Here we go. And and it's a quotient rule. It's a quotient rule. So the derivative of the top with respect to x is negative 3. Write down the bottom, multiplied by 2y, minus, write down the top, a negative 3x, multiplied by the derivative of the bottom. The derivative of the bottom is just a 2, but because it's a y term, it's 2 dy dx. That's an implicit derivative of the bottom, all over the denominator squared, 4y squared. So there's my second derivative. It's kind of interesting. The second derivative has x's and y's in it, and it has the first derivative in it. If we want to simplify it, I'll move over here, and let's talk about simplifying it. That's a negative 6y. That's a positive 6x multiplied by the dy dx. But hold on a minute. The dy dx was right here, or here it was simplified. So I'm going to replace the dy dx with what it is. It's negative 3x over 2y. Negative 3x over 2y. All over that 4y squared. All right, let's do a little more cleaning up here. Again, here's the second derivative. This is it. It's a negative 6y. I guess that's a negative 18x squared over 2y. I guess I could have simplified that. Let's do that. The 2 goes into that 18, 9. That's cancel the 2, right? 9x squared over y. All over this 4y squared. And that's okay. That's kind of simplified. The truth is what we have is a fraction within a fraction. You know what I want to do? The easiest way to simplify that would be multiply the whole numerator by a y. And that's legal if you multiply the denominator by a y. So here we go. The second derivative is, if I distribute this y, negative 6y squared. This y cancels, so negative 9x squared all over 4y cubed. So there we go, the second derivative of this relationship. You know, just a quick reminder, the second derivative doesn't mean much to us. It's a little tough, it's a little tricky to get it. Not too bad though, but it has this first derivative. We replace it with what the first derivative is, and that helps simplify the second derivative. Just want to remind you, if the function y is distance or position and x is time, then the first derivative, dy dx, is velocity. The change in distance over time, the change in position over time, that would be the velocity at any moment, an instantaneous velocity. And the second derivative of y with respect to x, if x is time and y is distance or position, then the second derivative is acceleration. So the instantaneous acceleration at any moment. All right, so we'll do some more stuff. We got to do some word problems next, or actually we got to work on the inverse trig functions next. Thank you for watching and listening. Do some homework.